So just to pull this all together and make a couple of points absolutely clearly, you'll have noticed that I've sometimes been calling the subsets in a partition blocks, and this is standard terminology. Other things to notice: we can use the definition of partition to take an infinite set and partition it. We saw that with our integers. And we can partition an infinite set into an infinite number of subsets. So we also saw that. The thing to note is that if you have a finite set, obviously you're not going to be able to partition it into an infinite number of subsets because you're limited by the number of elements that you have. So now that we have that, we can start tackling problems like the one we saw at the beginning. We're going to start a little simpler though. So let's have a look at this problem. We are told that the third year computer science majors take one and only one of the following three courses: cryptography, data structures, or JavaScript. So every student has to pick. They have to take one, they can't take two or three. And we're told that the class lists for cryptography, data structures, and JavaScript have 75, 60, and 55 students respectively. And the question we want to ask is, how many third year CS majors are there? So there are various ways that one could tackle this problem, but we might as well use what we've already developed, so use the idea of partitions. So we're thinking about a set of students, and what we'd like to know is what is the size of that set of third year computer science majors. So I'm thinking of my universe here as my third year comp sci majors. And we have some information. We know that every single student is taking one of these three courses, and only one. So our universe is partitioned into 3 bits: those taking cryptography, those taking data structure, and those taking JavaScript. And in fact, we know how many students are in each bit of these. There are 75 students in cryptography, 60 in data structures, and 55 in JavaScript. And since those are all the students in third year, because every student has to take one, and there are no students taking 2 of the courses, we can work straight out that the size of our universe must be the size of the sum of each of our blocks in our partition. So if we do some quick addition there, we'll see that this is 190. So we know that there are 190 third year computer science majors. So let's formalize this idea as what's called the basic law of addition. And the basic law of addition says, if we have a finite set that's partitioned into a bunch of blocks, then we can find the size of the overall set by just adding up the size of each of the partitions. But it's really important here, the thing that's kind of crucial is that we have at all intersections of our subsets are empty. So that's one of the aspects of being a partition that makes this work. You can see that it wouldn't work if we had 2 sets in here that had an intersection that was non-empty, because then we'd do some double counting. So here's just another way of reframing what we just said. We've got A as a finite set divided up into a set of subsets whose union gives us A, and here we're saying our intersections, and we should have an empty set over there, where our I intersection AJ is empty set whenever they're not the same set. Then we can have this basic law of addition. So that rule works very nicely if we are given information about a set that is partitioned. But what happens if the set isn't partitioned? And in particular, we want to think about what happens if we have a set that has subsets that we have information about, but the intersection of the subsets is non-zero, is non-empty. So here's an example of that kind of problem. So we've got 50 patients admitted to a hospital. We know that 25 are diagnosed with pneumonia, 30 with bronchitis, and 10 are diagnosed as having both pneumonia and bronchitis. And the first question we'd like to ask is how many patients are diagnosed with pneumonia, bronchitis, or both? And then finally we want to ask how many have neither pneumonia or bronchitis. So it's helpful in this kind of question to think about the information that we have and also draw a Venn diagram. So I'm going to have my universe here as usual, and I'm just going to say my universe is equal to the set of admitted patients. And the information that I have is that we had 50 patients who were admitted. Then the next thing I know is I have a set of those patients who are diagnosed with pneumonia. I'm going to call that P. And I know that the set of patients, so this is the ones with pneumonia, and I know that there were 25 of them. And then I also know that we had some patients who were admitted with bronchitis, so I'm going to call that set B, and this is patients with bronchitis, and we have the information that there were 30 of those. And finally, we have a bit more information. We know that if I look at all the patients who are admitted, that the intersection of those who have pneumonia and those who have bronchitis, so the ones who have both, is 10 patients. So it might be worth having just a little slight look at in different colors. So my set P is of size 25. My set B has size 30, and my intersection of the two is size 10. And I'm sure at school you worked with problems like this, and you can certainly just do it by putting the numbers in and doing some calculations, but we're actually going to develop a rule that works for this kind of problem. So the question we want to ask is, what is the set that we're looking for here whose size we want to find? Well, we want the patients who are diagnosed with pneumonia or bronchitis or both. So what we'd like to know is the size of P union B. So if we have a look in our diagram at P union B, we can't just take the size of P plus the size of B, because we're going to have some people who have both, and those people are going to be double counted, so we need to subtract off our repeats. It might be helpful to look at this a slightly different way. I'm going to label these three regions A, B, and C, and then if I have a look, if I'm taking the size of P, what I'm really doing is taking the size of the region A plus the size of the region B, and then when I add B, I'm adding the size of the region B plus the size of the region C, and this is where we can see that we've double counted our intersection. So in order to make this correct, I need to subtract off the repeats, which are region B, but region B is really the size of, so our region B is really the intersection. So finally we have, to work out the size of P union B, we have size of P, size of B, minus the size of their intersection, because those were the double counted. And if we plug in the numbers that we know, this gives us 50 plus, sorry, not 50, that should be 25 plus 30 minus 10, and that gives us 45. So we know that there are 45 patients who have pneumonia, bronchitis, or possibly both. And then we can work out the number of patients who are not diagnosed with pneumonia or bronchitis, and that must be our total number of patients less the ones that have one or both of those, so we have 5. So you might have, as I said, have worked on these kinds of problems in a different way, and that's fine, you can use it to check. But the thing that's useful about this technique is it's generalizable. So let's have a look at that. The method that we developed is called the Law of Inclusion Exclusion. And we really figured out this formula over here. If I want to find the size of the union of 2 sets, then the way I do that is I take the size of the one set plus the size of the other, and I subtract off their intersection. Notice that this actually works perfectly well if our 2 sets are disjoint, so their intersection is 0. Then this term just becomes 0, and as you would expect, we just add the sizes of the 2 sets. We can actually extend the inclusion-exclusion law to 3 sets. And we're going to have a look at that in the next example, but here's the rule. So, as usual, we start by adding together the sizes of the sets, but then we need to subtract off various intersections, but it's going to turn out that actually we need to add some back in because we'll have subtracted off too much. So we'll have a look at that in the next example. So we're finally at the point where we can look at our original question, and we're going to use our 3-set law of inclusion and exclusion. So how do we set it up? We know that we've got a set of second-year computer science majors, and they're each taking at least one of the following courses: algorithms, logic, and compiler construction. So what I'm going to do is I'm going to take my universe as a set of all students, and then within that we've got the students who take algorithms, and we know that there are 75 of those. So we know that the size of A is 75, and we know that we've got some students taking logic, which I'm going to call L, and we know that the size of that is 60, and we've also got some students who are taking compiler construction. So our C is those taking compiler construction, and we know that we have 55 of those. And then if we do some more reading, we see that 10 of our second years took all 3 courses. So that tells us that the size of A intersection L intersection C, which is this little bit over here, is equal to 10. And we know that 25 took algorithms and logic design. So we know that 25 took both algorithms and logic. So we know that A intersection L has 25. And we know that 12 took algorithms and compiler, so that's this intersection over here. Algorithms and compiler construction gives us 12. And finally, we know that we have 15 took logic and compiler construction. So we have logic and compiler construction is 15. And what we really want to work out is how many students took, how many second year computer science students are there. So if we want to put that, let's try and find a nicer color. So we want how many computer science majors are there. Well, we know that all the students took at least one of these. So what we really want is the union of those three courses. So what we want is we want the size of the union of those taking algorithms, those taking logic design, and those taking compiler construction. And you could work through this in the way that you did it at school, but we can actually go back and appeal to our three-set inclusion exclusion law, which says we must add up the size of each of the sets, subtract off the size of each intersection, and then add the triple intersection. So if we work this out, we're going to say this is going to be the size of A plus the size of L plus the size of C. Then we're going to subtract off the size of A intersection L, the size of A intersection C, and the size of L intersection C. But if we only did that, then our little middle bit over here would actually not be counted at all. You can check that for yourself. So we're going to add back in the size of the intersection. So if we plug that all together, we get 75 plus 60 plus 55 minus 25. So I'm going to put this together. Minus, so we're subtracting off our intersections. A intersection C is 12, L intersection C is 15. And then we're adding on our overall intersection, which is 10. And if you work that out, then you will find out that there are 148 students. One way to see that this is giving us the right answer is to divide our set up into a partition. So we actually did this with the previous example. So I'm going to label each of these sections separately, and technically we have an H over here, but we're not going to worry about that. And let's see, we know that if we think about each of these little sections, which I'm thinking of as a block in a partition, if I add up the size of all of those, then I'll have, so I'm thinking of adding up A through G, then I'll have the right number of elements in second year. So let's see what's happening over here. If I take the size of A, that's really the size of little a plus little b plus d plus e. And if I take the size of L, that's going to be the size of C plus the size of little b plus the size of little d plus the size of F. And if I look at C, that's going to give me, so this is big C, that's the size of little e plus the size of little d plus the size of little f plus the size of little g. And now notice that we've got some double counting going on here. So, for example, B gets counted both when I take the size of A and the size of L. E gets counted twice as well. F gets counted twice. And in fact, we have D, which is getting counted 3 times. But we only want to count each region once, so we need to subtract off some stuff. And that's why we work over here. A intersection L is going to subtract off B and D, and A intersection C is going to subtract off the size of E and the size of D, and L intersection C is going to subtract off D and F. But now, if we have a look at this, this is correct because we've sorted out the double counting of B. We've sorted out the double counting of E. We've sorted out the double counting of F. But now we've actually subtracted off D too many times, because here we had a D and a D and a D, and now we've subtracted those all off. But we still need to count D. So that's why we add in this bit over here, which is D. And now if you have a look at everything that we've added together, we've got A and B and C, and we've got D, and where's our E? There's our E and our F and our G. So that's one way of looking at how this works. I suggest you work through quite a few examples of these and find the method that works best for you. So try several different things, try and answer these questions in different ways, and find out how your brain works best for these kinds of problems.